So today's material, if you go to my website, scroll all the way down to the bottom to GopherCon Turkey, and this is the material, so we can read along. So thank you very much to the organizers who've given me a little bit of extra time. I'm going to try and get this done in an hour, but I think we might take a little bit longer, but we'll get through as much as we can. So the thesis is that JSON is very important. This is probably not surprising. We're all experienced programmers here. And whether you work at the highest level, writing business applications or delivering mobile applications to users, or you work at the lowest level, just someone like me who works on a language implementation or works on libraries or containers or platforms, things like that, you probably can't escape JSON or YAML or TOML or any of those other languages, but JSON is pretty hard to miss. Now, in Go, we have a fairly comprehensive standard library. We've had the Encoding Json package since, certainly since I came to the language 10 years ago. And so JSON is very important, and we're very lucky that along with HTTP, we have JSON support in the language. But as important as JSON is, and as kind of central it is to the work that we do as programmers, JSON is really expensive. Throughout the last 10 years of Go, we've seen the Encoding Json package improve in leaps and bounds. Sometimes these improvements have been very big. For example, when we moved away from segmented stacks in Go 1.13, that delivered a great improvement because the segmented stacks did not play well with the recursive nature of Json decoding. But one of the things that has inspired me to look into this area recently is that certainly in the 1.15 cycle, and we just saw the release candidate earlier today, there were two performance improvements which were landed and then had to be rolled back because they broke kind of subtle behavior that people were relying on. And so, as important as the performance of JSON is, we seem to be running up against the natural limits of what we can do with the API that's been specified. Now, this is obviously not a new idea. In the Go ecosystem, there are a bunch of alternate JSON libraries, MegaJSON, FastJSON, there are others. I'm sorry if I can't remember all your names. And in looking into them and looking into what their ideas were, I noticed that they were maintained by a small number of people. And so this suggested to me that this idea of exploring alternative JSON implementations is not something that needs a giant team and many years of development. So I figured this was probably it's probably a valuable area to explore. Now, let's start at the end. At the end, these are kind of the results that I have so far. At the lowest level, package JSON can stream JSON without allocation. If you know the output from encoding benchmark, we can stream through these kind of sample JSON files of various kinds without allocation, and this is kind of the key takeaway. At the next level, we have a tokenizing API which mirrors encoding JSON, and comparing to the various inputs, package JSON versus encoding JSON, we're about 2 to 3 times faster. 33 megabytes versus 100 megabytes a second, 82 versus 330. Equally with significantly fewer allocations. Now, obviously, allocations are very important to the overall performance of this API. And so if you're prepared to accept an alternate API, and we'll talk about that a little bit later in the presentation, package JSON, we can deliver performance with comparable output, somewhere between 8 and 10 times faster. So looking at encoding JSON versus package JSON, 8-10 times faster. 86 megasecond versus nearly 800. And in terms of the allocations, they're virtually no comparison. This is almost a fixed overhead, and I do know where these come from. Removing them is tricky, but hopefully you'll compare, like, what is that, 23 million bytes allocated versus 240. 6 orders of magnitude small, 5 orders of magnitude smaller. Now, going up a little bit further, normally when we're decoding JSON, we don't just kind of talk about the tokens. We go to and from Go objects. And so for an example of decoding into an empty interface, so basically you let the JSON decoder build the map of string to interface again and again and again. We're somewhere between 30 to 50% faster. And you see, as every time we build up these levels, the improvements get less and less, which was a little bit disappointing in the end. But definitely for what turned out to be about a couple of weeks' work, to be able to find 30 to 50% more performance for the same API was pretty promising. And so this is the story of how I went about this. And we're going to talk a little bit about JSON, but more about design and a little bit about optimization. So when I sat down to work on package JSON, an alternate JSON decoder, I kind of set myself some ground rules, some design constraints. And the first one is it has to be reasonably compatible with the encoding JSON package. We offer both the same high-level decoder API, token and decode unmarshal, that offers high throughput and usually both reduced allocations. So a success criteria is that at least for the casual user, it should be possible to just replace their import from encoding JSON to package JSON, and the code still works. Spoiler alert, we're not there yet. Decoding into Go objects is very nuanced. But to the degree that what we have is implemented now, it holds up the promise of both high throughput and reduced allocations. The second constraint that I set was we have to support streaming operations. And the reason I set this is, well, this is the API that Encoded Json presents. It takes IO readers, so we have to support that. But at kind of more at an abstract level, it's nice if you can have the entire input in memory. Like if you can read all the JSON off disk or read it all off the network or get it out of the database or wherever it comes from and hold it all in memory, because then tokenizing it is actually quite straightforward. But the trick there is that unfortunately we live in the real world where your input sizes are usually not known. Like when someone streams you some JSON, uploading JSON via web request or something like that, or they just pass you an open file handler, you don't know how much data is in there. What you're accepting then is, I will read as much data as you send me. If you upload 5 gigabytes, I'll read 5 gigabytes and I'll hold it in memory while I'm processing it. And doing that is an availability risk. You give the remote end the ability to fill up your address space, to run you out of memory, to force excessive GCs on you. Also, buffering before processing infuses latency. If you can't start processing the JSON until you have it all in memory, it means you must read it all into memory. Now, if that happens very slowly or it's coming over some kind of upload process, that adds latency. You can't start working on that until you have the whole thing in memory. This package, because we support IO reader as the base import source, as I said, which is required for the first requirement, reading data from the network and kind of processing it happen effectively at the same time because of buffering and things like that. So supporting streaming operations was a nice to have, and something that when I looked around at other alternate JSON implementations, they didn't have this. They expected you to have a byte slice of memory. And the last one is, and this is a point I'm going to keep coming back to, we want to either be allocation free or those allocations be from a fixed buffer. Again, because if they're not, then that's an availability risk. You let the remote side fill up your memory if you don't have a bound on that buffer. And also, as you'll see, allocations are the key to performance. So let's talk about the time complexity of this problem. I won't spend too much time on this, but effectively, if we need to, JSON doesn't have length markers. It's not like Ethernet. It's not like protobuf. When you start to read some data off the network, it doesn't come with a header that says, "I'm now going to send you 50 bytes," which means you lack the ability to skip through the file. You have to read it all to process it all. And so that means that the absolute lowest bounds on decoding some JSON is the time it takes to read it all in. This might seem self-evident, but given that you can't skip ahead in a JSON file, just like you can't skip ahead in a zip file or a tar file, it means the time to process the last element in the file includes the time to read the whole thing. Now, obviously reading isn't enough. We need to follow the JSON state machine to make sure that the tokens are valid in correct orders. And so the lowest bounds of doing this work is reading the file and parsing the file where n is the number of bytes in the file. This is important because it comes back to how we're going to estimate how what we're doing. So there are other costs, obviously, if we have to allocate memory or for each read or for each processing of this byte. That means the overhead is bounded by the size of the input. The larger the file, the larger the overhead. It's not great. I want to avoid that. Now, as I've said, the base time to do this work is how long to read and process n bytes of input. So ideally, for each byte, each individual byte in there, we want to only process it once. If we touch the same byte more than once, that adds overhead because it gives us a constant scaling factor. Instead of n, it becomes 2n or 3n, or however many times we touch the data. There's a story that is sometimes told about the reason, one of the justifications for creating Go, which is the C++ include model, where each byte in a header file explodes to something like 8,000 times its size once it's been included and included and included and included. So clearly, we want to limit the number of times we go around and read and process the same byte. Now, just like we don't want to process each byte more than once, we obviously want to avoid processing each token more than once. So we want to do, whenever for each JSON token, and we'll see that next, we only want to kind of look at it and make a decision about its validity and its length and all its other properties just once. Now, as in any kind of scanning or processing, there's going to be function calls, and the number of times they're called and kind of their sequence is obviously determined by the input. So ideally, we want to use the minimum number of function calls per byte or per token. Now, in terms of what we consider the hot path, compared to encoding JSON, which uses one function call per byte read, it kind of reads a character, calls something of the state machine, makes a decision, reads the next character. We do a little bit better. Package JSON effectively makes this inner loop one per token, and so we want to. So ideally, if we did nothing else than just move from one function call per byte to one function call per token, we'd be coming out ahead. But there are actually more benefits in there. We want to limit the copies. If we design into our program, if we build a design that limits the need to copy data around, then we limit the number of times we revisit a byte, because copying something means you read it, you make a copy over there, and obviously if you're going to make a copy, it's because you're going to go and read that copy sometime later. So if we limit the copying, we limit the number of times we revisit a byte. Also, we want to limit allocations. You'll see as we go through here, allocations are the killer of performance. And one of the ways that we can know that we're limiting allocations is by not copying anything. Because if we don't copy anything, we don't have to create a place to copy it to. Logically, the only kind of copying we could do is to copy over ourselves, which we don't do. And just to talk a little bit about allocation and why I'm harping on this so much, is that allocation has overhead. In any garbage, not just garbage collector, but any kind of heap-based memory allocator, be it garbage collected or malloc-based or however you choose, there's always some overhead with the bookkeeping of the allocation. And equally, the heap is a shared resource. In a multi-threaded or multi-process program, eventually you're going to have to coordinate on who owns which area of the heap. This happens in every allocator. And obviously, coordination means brings you up against Amdahl's law, which means that the more that you have to coordinate for the heap, the more that overhead grows. And equally on the other side, when you go to free those allocations, enormous amounts of work has been put into different allocators and background garbage collection and concurrent garbage collection. But quite simply, the cheapest garbage collector is to not do it at all. Nothing is faster than doing no work. So if we limit the number of allocations, we limit the amount we have to clean up, and we limit the amount of performance effectively we have to move to the side for that bookkeeping. So that's the overall design goal. And I wanted to open with that because this is a process that I think, whether you're writing a JSON decoder, whether you're writing a database server, whether you're writing a mobile application, like whatever application you're doing, you should have those discussions about what are the constraints and what are the major code paths within the application. And you should probably try and do that up front rather than discovering it organically, because that could potentially be too late to do anything about it. So we all know what JSON is. I won't dwell on this. JSON is a stream of tokens. What's a token? If we take this input here, we have curly brace, the string A, a colon, the literal number 1, a comma, the string B, the colon, the identifier true, a comma, string, comma, colon, square brace for arrays signifying ordered list, numbers, string, the literal null. These are all tokens. I'm moving quickly through here because I'm sure everyone can has seen JSON of this kind already. Now, if we wanted to process this input using encoding JSON, we come up with this example. We have our input. We construct a new decoder, and the decoder takes an IO reader. So we use strings new reader to convert the string literal input into a reader. And then we enter into an infinite loop where we go round and round asking for the next token. We check that we haven't got an error, because when we run out of tokens, this returns IOEOF. If we haven't hit the error, then we print out the value of the token as well as its type. And so this is our input here. You saw me kind of express it in words here. And let's look at what we get when we actually run the program. We get a curly brace, which is a delimiter. We get A, which is of type string. We get 1, which is a float, because all numbers in JSON are floats. We get another string. We get the Boolean true. We get a string. We get a delimiter. We get a comma. We get the string 2. We actually get a nil, which is a nil value in a nil type. And how does this magic work? How does this work? It works because toke here, tok, is of type empty interface. So it can contain both the value, A, the string, 1, the number, B, the string, true, the Boolean, as well as its type. I mean, this is the magic of interfaces, that they record the type of the concrete type of the value placed into them, as well as the actual value itself. And this is super convenient, because now you can imagine a younger Rob Pike or Russ Cox sitting down with a very proto version of Go and writing an API like this and saying, look, instead of just like bits of a string, we actually get real typed values. Isn't this great? We can do type switches on them. We can assign them. They're real typed values. That's great. No one's going to mistake the number one for the string one, all these things. But there's a cost to this convenience. This footnote here is a link to a comment by Brad Fitzpatrick, who called this API a garbage factory. And to explain why he would make such a claim, let's just take a little bit of history through Go. If we create a byte slice of 10 bytes, we call it B, and then we convert this the byte slice B to a string, the compiler is going to make a copy of it. And the reason it's going to make a copy of it is that strings are immutable. If a string and a byte shared the same backing data, then if we change the contents of B, we would change the contents of the string if they both pointed to the same data on the heap. Strings are immutable. We can't allow that. So every time you see a conversion like this, you know that it makes a copy. Now let's look at the inputs into Json Decoder. We saw an example of it earlier before. New Decoder takes an IO reader. What's the definition of an IO reader? Well, an IO reader has a read method which takes a slice of bytes and returns the number of bytes it read into your buffer and an error. And so now, just with this explanation, without opening up the code or looking at anything, I can tell you a few things about what's going to happen. We know the input stream is a slice of bytes, and the outputs are runes and floats and bools and other types. So at a minimum, the string hello is going to, at some point, be read as or converted into the byte slice, HELLO, and that byte slice is going to be copied into a string because, as we said, Json Decoder returns you a typed value. So we go from the literal string hello to a reader, which is going to pass it up to New Decoder as a slice of bytes, or it's going to read it into the slice that New Decoder passes it. And then New Decoder is going to convert it back into a string. And so without looking at any of the code, like I don't want to spend too much time on this, but I don't need to look at the code to tell you that these allocations will happen because it's right there using the knowledge of the spec and using the types that we can see that the input and output of Json Decoder. So that means this API, and the reason why Brad called it a garbage factory is that means one allocation per token at least. But it gets worse. TOC is decoder token is an interface value, and interfaces are this magic two-word structure which contains a field for the type and a field for the data. Don't worry too much about uint pointer. That's just the Go way of saying the native memory size. So 4 bytes on 386, 8 bytes on AMD 64. Now, so the interface can hold the type and the data. And so type is just a number that says this is the ordinal type we've given to the ordinal number we've given to this type. And the data is a single word, 8 bytes in this case, that has to somehow hold any piece of data that we put into it, from a true or false all the way up to a complicated structure. How's it going to do that? Well, this is part of the other magic of Go. If any value that is put into here has to go on the heap, and we put a pointer to it here. The reason why we do this is both anything bigger than a machine word won't fit there, so we have to store it on the heap, and then we'll put its address in there because that will fit. The other one is garbage collection, and this is a change that happened around Go 1.6, might have been a bit earlier. It has been a little bit rolled back in Go 1.15, but not to the point that it matters for this discussion. But to explain what is happening, we have an empty interface called X, and we assign the integer 1 to it. Now, we assign the string 1 to x. And what has had to happen here is that the type has had to go from integer to string, and the data has had to go from the value 1 to the pointer to the string 1. And this means that two things have had to happen simultaneously. We've had to update the type field and the data field at the same time. And this is very problematic because Go programs are concurrent. And there's no way that there are no shipping CPUs that let us update more than one word in memory at a time. So part of the reason why it has to be a pointer is because the garbage collector is working in the background there, and it could potentially see this interface in an intermediate step where its type has gone from integer to string, but its value is still the old integer value 1. The way they work around this is by making everything be a pointer, because the garbage collector knows more about pointers, and apparently it's not a problem to do that. And there are more problems that because the string structure is bigger than a word, that doesn't fit in the one word structure here. So the final result is that from the string input, which effectively strings reader converts from strings to slice of bytes to the decoder, we write a little benchmark here. Just decoding the single JSON token hello allocates 37 bytes in 3 allocations every time through that loop. So that's a real world cost of just reading the simplest JSON token, which is a string. We're not decoding it into, we're not unmarshalling into anything. We're literally just give me the token. I gave you the input, just give it back to me. 3 allocations. So as I mentioned at the top, a lot of the performance improvements of this come from changing the rules of the game, changing the API. The first, and so how are we going to go about doing this? Let's look at the sequence of tokens we're dealing with: curly, string, comma, colon, string, boolean, C, angle bracket, things like that. Now, this is not my idea. This is actually one used inside Encoding Json, and I've seen it in a bunch of other JSON libraries. But each of them make the observation that each of the different valid tokens inside JSON can be uniquely identified by its first character. If its first character is one of the curly braces, it's the start of a map. If it's a square brace, it's the start or end of an array. The word true always starts with lowercase t, and so can only be followed by R, U, and E. F for false, N for null. All strings, irrespective of their contents, start with a quote. And if you can arrange it, that means the only things left over are hyphen and the numbers 0 through 9. And so the first improvement that we make with our alternate next token API is, rather than converting the byte slice to a typed value, we just return the token sliced straight from the input, which is a simple subslice. So if we compare this to the version you saw earlier, same input, we're just using package JSON now, so same constructor. We're using our new token API to show the improved performance. And you see, instead of typed values, we just get byte slices that are effectively slicing the relevant parts out of the JSON. Now, there are a few subtleties with this API. Obviously, because it's a subslice of the input, not a copy, there are restrictions on how long the output is valid for. In the case above here, we're reading from a constant, so we have the full input here, but you can imagine if you're reading from a network or something like that, as you read forward in the file, you reuse the buffer. So previous tokens are not valid anymore. Now, it turns out that we have APIs like this. The very popular Buffer.io scanner has this API. I believe that Database SQL also has this API. So while it is, in principle, less convenient to work with, in practice, it's a very common pattern to say this buffer is only valid for a certain amount of time. If you need it after that, make your own copy. And that's really important because that means that rather than the API allocating for you, it pushes the cost back to you as the caller to make that decision. Now, obviously, sometimes you don't just want it as a byte slice, you want it actually as a type number. But it turns out that doing this work to go from, just make that a bit bigger, to go from next token to the token API that is exported by Encoding Json can be expressed in less than a dozen lines of code. So if you didn't want to do this work and you wanted to go back to the original token API, it's not a lot of work. So let's talk about what that. We don't have a benchmark for that yet, but we'll get to that in a second. So now we have some ideas about how we can efficiently do that lowest level tokenization of the data. Let's talk about how actually to get that data into memory. The traditional way, in fact, pretty much the only way of getting that data will be through an IO reader. Now, there are some tricks with JSON because of the way that the reader API works. For example, you can go one byte at a time, like look at each character and say, okay, if I'm looking for the start of a string, I can look at the character. Okay, that's the start of the string. And then, okay, now I know I'm in string mode. I can start to take each character as it's handed to me and put them on my side and build a buffer which holds my string until I reach the end of the token. Or you can read into a buffer, and then you have just a slice of bytes which potentially contains the start and the end of your token. If you're lucky, that's great. If you're not lucky, you have the start of a token but not the end, and you hit the end of your buffer, and so you need to go back and read some more. And so you need to do a lot of management of like, okay, do I go and create another buffer and then either stitch them together or kind of manage the transition? There's a lot of bookkeeping there with dealing with the what do I do if I have partial input in that buffer. So IOReader provides a very simple interface, but sometimes it's not very convenient for this work. Encoding Json does a combination of both the character at a time and buffer at a time, offering with a smattering of sync.pool to try and reuse buffers transparently. And we saw the results ourselves. Now, the work that gave me the inspiration to try this were ideas by people like Philip Pearl and Steven Schnemenhofer, who's a D programmer. And I'm using Schnemenhofer's IO pipe here idea, but Phil Pearl's byte reader buffer is the same thing here. Effectively, what we want is we want an abstraction over IO reader. And various people call it various things, but I'm calling it a window. Effectively, I want a window over this input. Let's just say the highlighted area here is our window. And that's what I can get. And I can look in that window and I can do two things. One, I can release characters from the front. So imagine that the window shrinks from the front, or I can grow it by reading more data. So it extends out this way. And this is the API that we get. We have release, which says I'm done with data at the front. We have extend, which says grow the window by reading more data from the underlying source. And window, so just give me what I'm currently looking at here. And to give an example of this and kind of start to tie this together, let's talk about how you would use this concept. Because one of the most important parts about parsing JSON is ignoring whitespace. Spaces, tabs, new lines, carriage returns can occur anywhere inside JSON, and they are non-normative. They are ignored. So the actual tokenization work of every JSON token starts with looking for the first non-white space character. So let's talk about how we use the byte reader idea to do something simple as looking for white space. So in this count white space function, n is the number of white space characters, w is the window, and because window is just a byte slice, we can use the classic for range idiom over that. And so for each character in the window, if it's a white space, we increment the counter, otherwise we don't. Now, when we get to the end of the for range loop, we've gone all the way through the byte slice which represents the window, and so we can say we release it. We've read all of that. We call extend, which effectively grows the window by some amount. If it can't grow it at all, that means we've hit the end of the file, and we're done. Otherwise, we replace the window with the new one. We go around, we do it again. Now, the reason that I'm starting here is this represents the minimum amount of work you would need to do to reasonably parse any file, and it conforms to the time constraints that we set earlier. We visit each character once. We make a function call for each of them, and we do some work. We count the number of white space characters. Any useful JSON decoder cannot go faster than this. The only way you could go faster than this would be to read the data and ignore it. So this represents the baseline. Like this is the fastest you can go. This is we talked about just this is white space function. This is the one that the Encoding Json package has, which is very clever. It says if the character isn't less than space, because of the way ASCII works, then quite clearly it's not white space, because space, tab, new line, and carriage return all exist higher and lower in the ASCII table. So this is quite a clever optimization. But I did some research. You can follow that link to a repo which compares various methods, and it turns out that using an array of basically trues and falses is reliably the fastest. When I say reliably, this method is unpredictable because of branch prediction. Depending on the input, some inputs that have a lot of white space cause the CPU to believe CPU's branch predictor to behave in one way. Data that has has less white space causes the other way. There's no. It's very difficult to tune this kind of expression to always work well for every input. If we have a look at Canada, for example, has virtually no white space. Code has virtually no white space. CSIM and Twitter are effectively, they've been fed through JQ. They have a lot of white space. But for each of them, we see that the baseline speed is just over 2 gigabytes a second to read and count the number of white space characters in the input. And these are 2-3 megabyte files. So this is our baseline. This is the fastest that any reasonable JSON processor can go using this model. And the reason why I start with this number is that the only way to go faster than this is to do no work. And if we do no work, we're not actually parsing anything. So this represents a baseline of which we can compare the performance of the code that we write to say how close are we to the theoretical maximum. So now we're starting to get some of the pieces together. We can tell which characters are tokens, which are simply white spaces. So let's talk about how we break up those tokens. So this is the scanner.next function, which effectively you call it to get the next token. It skips over the white space and returns you the next token. So the operation of this is that we release the previous token, we mark that buffer is not needed. We do some housekeeping to set our pointer back to 0. We call token, which gives us the first character of the next token. We just switch on that. If it's a kind of punctuation type structural, start and colon, blah, 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 they all have length of 1. True, false, sweet. So we basically, we get the first character, and just like we said, the first character tells us what type it is. We then switch on that. So as I said, skips over white space, determines the first character, then reads the rest of the token. So let's talk about this token function. And if you compare it to the earlier count white space functions, there's a lot of similarity. We grab the window, we range over the window. If it's a white space character, we need to move that marker that says the white space, the character where the character starts. We move the marker on, and we go around through the loop again. Otherwise, if it's not white space, then we have found the start of a token. So we throw away that intermediate white space. We set our counter back to 0 to say we now have aligned the start of the window with the first character. And because we have the character conveniently in a local variable, we just return that. Otherwise, we need to grow the window. And fortunately, we don't need to start scanning the whole window again. We've scanned it up to this pos line. So conveniently, we only need to do the new characters we've read into the window. Let's talk a little bit about that, how that works. Now, there are some interesting kind of side effects from this style of IO processing. First of all, you note the lack of error handling. There's no if error not equal nil crap through this code. It's not in the inner part of the loop. It only happens when we have to read more data because the window doesn't return an error. It's just a byte slice. So we only need to check for errors when we need to grow the window. Now, extend hides that process of growing, shuffling, refilling the buffer, and simply just returns the number of characters successfully read. So if there was an error, that number's going to be 0. We just return that. As we see, we say extend equals 0, reach the end of file, we return. Internally, the extend keeps that error, and we can grab it later, just like the buffer.io scanner API. And the key thing here is that extend is not in the hot path. So we don't need to optimize it. Its performance is a function of the buffer it works with, and I've done a lot of experimentation with this, and quite honestly, a buffer of 8K, which is reused over and over again, reduces the amount of time spent in extend below the level which can be measured. So we're not calling through an interface for every character. We're not even calling through an interface for every token. We're only calling through an interface every time we empty the buffer. And this gives the caller much more flexibility, because if they're spending too much time in extend, they just give it a bigger buffer. So let's talk about performance. How fast does this code go? "500 megasecond, 600, 600, less than 500. So compare that to the 2 gig that we saw earlier. We're somewhere between 1/4 and 2/5 of our baseline. So this is really useful. We both have a number and we have a target to optimize towards. So let's talk about optimizing this code. The first improvement we can make is, let's have a look at the amount of work being spent to keep track of the kind of cursor position within the buffer, which is this pos value. Every time through the loop, we either increment it or set it back to 0. But if you look up here, its value is only ever used on entry and exit from the code. Before we call token, it's always set to 0. And before we leave token, it's always reset to 0. So knowing that it's 0 on entry and 0 on exit, we can actually rewrite this because we don't need to coordinate it. We can just keep it as a local value inside token because, well, it's always 0 on inside and out, so it has no effect. Now, and it turns out that the effect of this is pretty impressive. We saw 36% improvement, 50% speed up, nearly 40% speed up, just from moving from keeping s.pos in the field and replacing it with a local value. And you might think, oh, this is just a poor compiler optimization. Surely the compiler could pull s.pos into a register. And yes, it does. But if you look at the code here, there's no way for the compiler to predict when we're going to exit token. It could exit here or here. And so effectively, it's very difficult for it to, it can keep the value of s.pos in a register, but every time we change it, it has to write that register back to memory. And this is what we're seeing. This is the 30% to 30, 40% of performance we're leaving on the table. But all of those writes back to memory over and over again. Every single character causes a write back to memory. That just uses up memory bandwidth, that uses up instruction stream. Like those are instructions which ultimately every update of s.pos is finally overwritten with 0. So not only do they take time, can't be optimized away, but fundamentally they do nothing in the end. So by avoiding doing that work, we get that performance back. Now, why did this improve for some inputs but not others? It had no effect on Canada, didn't touch code, but CTIM and sample moved enormously. And it is to do with the number of white space characters. Canada has basically 33. CTIM has 1.2 million of them, about a third of the file is white space. And that meant that for files like Canada and code, we were calling into token, getting the window, starting this loop, immediately falling through, releasing the window, and returning back to the caller. Because there was no white space, we were paying the cost of doing the token function call for no value. Others that did have white space benefited from this because we went through this loop a bunch of times and then exited. But effectively, what we're seeing is the difference in speed up is related to the composition of the input. So let's talk about other things we can do to improve the performance of token. And to do that, we have to talk a little bit about inlining and how it works in Go. Now, inlining is the process of taking the contents of one function call and bringing it up into its caller. This unlocks compiler optimizations. This allows it to prove things which previously it couldn't. Now, normally compilers do this automatically. The Go compiler does this automatically. But in this case, it cannot. And we can use some flags to ask it why. And we see a few things. Well, the first one is that, for example, scanner.next is too complex. Inlining, if you're going to take code from one place to another, there's got to be a natural limit where if you just took too much, you just make everything big. You make the binaries too big for potentially no input. And so there's a cost limit, which we call the budget, that applies to each function. And so scanner.next is too complex. There's too much in it. There's no value in pulling into its caller. On the other hand, scanner.token is considered to be too hard. It contains a for loop, and at the moment, the inliner doesn't know how to inline for loops. That's just a limitation. So any function that has a for loop can't be inlined. But we know, let's go back to our constraints. We know scanner.next is called for each token in the input. This means that scanner.next freeze the window, and then call scanner.token for each token of input. Scanner.token can't be inlined. We saw why, because and therefore we're paying an extra function call. We call next calls token. We can't avoid either of those. And we're paying that for each token, whether there is white space or not. And this is why some of these benchmarks improved. Some of them got worse. That one actually, that's probably the same, 4% difference. Some of them improved, others didn't. And the reason is because of this function call overhead, which we can't optimize away. So in this case, given that we know that this is a fixed function call, we can do that inlining manually. And you have to take my word for it that this version is the previous version, just inlined manually. You can see the call to window. You can see the check for white space. We go around this loop until we run off the end of the white space. We have our first character in C, as we did before. We do our dispatch. And now, comparing that version to the previous uninlinable version, we get an improvement above all, because now we're not paying two function calls where one would do. So that improves the performance across all of the input. But it especially improves the performance across ones where there was no white space before. Canada and code. Canada itself picked up nearly 25% in just avoiding the function call. And this is basically where the scanner inside loop stands today. And we improved it a little bit, but nothing worth talking about here. Note that now Cytem is over 50% of the baseline. It's 1.1 gigabyte a second. Sample is nearly 75%. It's 1.46 gigabyte a second. We know that the theoretical maximum is around about 2 gig a second. So that's pretty good. And it's down to these optimizations. Finding a more reliable way of testing if a character is white space or not, that it plays better with the CPU's branch predictor. Avoiding these constant updates that have no effect, just wasted instructions. Doing manual inlining, because we figured out that actually scanner.next and scanner.token, even though it's nice to write small functions and break them down by class, effectively when they're in a loop, we were paying an extra function call per token. So manually inlining them, increase the indentation in the function, but the results speak for itself. And possibly the most kind of like galaxy brain part of this entirely was that most JSON contains white space. Even if it's generated by machines, templates, people love to write templates, and templates have white space in them. So most JSON is moderately optimized for readability even before you feed it through JQ. And it turns out the more white space there is, the faster we can decode it. Okay, two things to call out. One, we're getting close to the top of the hour, so I'm going to, we're doing relatively okay on time. It's probably about 20 minutes worth of material left here, but I'm mindful that we're in the overtime. Now, we have a scanner now which can tokenize the input. This is at base level at about 50 to 75% of the baseline that we established. But there are a few more things that we need to do to make this scanner fully functional. And the first one of those is validation. JSON is a state machine. It's not just about reading tokens correctly. The current token that you have in your hand determines the validity of the next one. For example, if you've read curly brace, the string username, then the only valid token is colon, because you're in the kind of map context. Nothing else is valid. So how do we do that? We need a kind of a state machine built on top of getting tokens. Let's have a crack at that. We have some constants here to track the state that we're in, the value or the string or colon or the object value. So that's you see array value colon, like tracking each of the different potential states that we can be in. And so we look back at next token and we see we see something that we can that represents the code that makes this all work. We have a call to scan.next, which gives us the next token. We make sure we just check we didn't hit the end of the file, and then based on the current state, we pass that token to a particular state method. So for in state value, we pass it a state value. For an object string, blah 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 blah. Nothing particularly surprising there. If we end or a state that we don't know, we just return IOF and say we're done. You can look at the code here to just trust that what it does. We don't have time to go through that. But let's look at the results of doing this. And again, now that we have an API which is comparable, we can compare package JSON against encoding JSON. And we see we are around about 8 to 10 times faster. But looking at these throughput numbers compared to our original 2 gig a second, maybe there's something we can do to improve. Central to the operation of next token is this switch statement. Depending on the state, we're going to go down each of these cases and then find the right state that we're in and then call the state method. And effectively what the compiler sees then is just a bunch of if then else cases. If this, call that. If this, call that. If this, call that. If then else. If then else. And so this is effectively what the compiler sees. And just to prove to you that this benchmark is comparing the previous version I showed you with this if then else version, and arguably they are the same. So I'm demonstrating that while we write this, the compiler actually sees this. And there are problems with this. This state set is not very large, but it's not small either. And the problem with this is that it's called unpredictable. The CPU can't predict what the next token will be, so it can't predict what is the value of each of these comparisons. You can do some reading, Google yourself on branch prediction and branch misprediction costs, but effectively, if the CPU guesses wrong, it's very expensive to clean up from making the wrong guess. And so this kind of input works very badly with branch predictors because it is effectively unpredictable. And that means that a lot of the pipelining that modern CPUs do goes to waste. And a lot of work in compile space goes into making switch more efficient. Now, one of the ways that you can do, although the Go compiler does not do this currently, would be to turn this into a table. And so effectively, there's a one-to-one mapping between the state value and the method you call. Method call, that state value method to call. Now, what if we could write this out as a table? If we could do something like this, which unfortunately we can't, but we can get close, then effectively we have an array of states to the method that we can call on them. And we could write something like this. And so now we don't have to do all those if, else, if, else, if, else. We literally look up the value in the table and call the method that is the result. And this is known as a computed goto. This is a very popular. This table-based dispatch is very important if you have a very dense state space. If you're writing bytecode interpreter or something like that, we have a lot of potential states of which you can't predict any pattern. This is an effective way to do it. Now, I said unfortunately we can't do this in Go. There's reasons why. They don't matter because I actually have a better version. And that is something known usually as a computed goto, which is, if you look at this table above, there's a pattern. Each state value maps again to exactly one method. So each time through the loop, we have this state value. What we actually want is the method that the value maps to. What if we could just store that method directly? Then we wouldn't need, then the state value would become the method itself. And in fact, we can do just that. using a thing called a method expression. It's not very common because in 1.1 we had the ability to capture the receiver a method, but it turns out it's quite a neat trick here. And again, this is a trick that I've borrowed from Encoding Json. So state goes from just being an enumeration to being the actual method that we want to call. And so that means that each time through the token, each time through next token, we just dispatch to the right method, which is stored in state. And if we look at the performance, it's not very good. In fact, it's worse. But it unlocks several optimizations. The first one, if we look here, we read the token, we check the token, we haven't reached the end of file, and then we pass the token to the right state method. It's good, dry code. But there are a few problems here. The first one is that, where's my words here? I don't know where they are. Yeah, the first one is that we're passing the token, so we have to pass the token down to the method. To each, the token is a byte slice, so that's three words on the call stack. That costs time, especially if we call it every token. The second one is that you note that we check, is the length of the token less than 1? Now, inside d.state, we have to do the same thing because we need to switch on the first character of the token. And because all of these things are bounce checked, the Go compiler has to insert a bounce check from there. And so the next trick that delivered some performance was to move this check from being done inside next token to inside each method. And you might think, oh, that's terrible. You've duplicated that code over and over again, and that's very true. But if you think what this allows the compiler to do, we don't have to pass the token in every time. So we save 3 words on the stack for each call start. Also, we have to do this check to say, is the token at least 1 character long? If not, we've run out of input. And so the compiler knows by this time that this condition is false. If we get to here, this condition is false. So therefore, the first element of token does exist, so it doesn't need to introduce the bounce check. And so we avoid the bounce check. We can actually prove that. If you don't trust me. And the last one, which was truly mind-blowing, is that previously this was slightly too large to inline. I have cannot inline next token. It's 145, exceeds the budget of 80. This version, which is just literally, it forwards from next token to dispatching to the current state, is small enough that it can be inlined. And so this means that when we as authors write something like this, what actually happens is the compiler optimizes it to a direct call to the current state method. So we have 3 things that are unlocked by this. We can reduce the amount of data we pass on the call stack for each call. We reduce the number of bounce checks that are emitted, and we reduce the number of function calls. It's not next token calls state object colon. It's literally the call to state object colon is made directly at the call site. So we reduce the number of function calls to get the next token to 1. And that was worth between 10 to 15% above, let's say 9 to 18% improvement over the previous version. I'm not going to talk about unmarshalling, mainly because it's still very much a work in progress. Most of the improvements we have are to do with the reduction in allocations. Once you get to that point, you spend more time in the reflect package and digging around in struct internals than actually doing data processing. It's just a lot of calls to the reflect package that neither encoding JSON nor package JSON can avoid. It's just part of the game. And so there isn't a lot to talk about here. So to close it out, these are the big thematic ideas that I want you to come away from this talk from. The first is that allocation affects performance. The garbage allocator, the garbage collector might be fast to allocate and efficient to collect. We've seen every release, it gets better and more capable, but doing no allocations will always be faster than the fastest garbage collector that could ever be written. Just not using it will always be faster. When dealing with data, the allocations can be the biggest performance cost of your algorithm. I talked about the ON, the ON allocations. Per token or per byte can be the limiting constraint on your algorithm. If you allocate even 1 byte of data per N of input, you can never go below that floor. You will never be able to avoid the cost of allocating and collecting that. In the version that I have, we have no allocations, so we are not constrained by that cost. API design influences performance. The Encoding Json Decoder API requires an allocation to be forced on the caller because of the way that it returns a typed value to you. And depending on the value it actually returns, that can be very expensive. In the case of strings, which are a very primitive data type that we think about, that actually counts to 3 allocations per call. By paying careful attention to the overheads per byte, so that's the different kind of reader, and per token, that's the function calls in that hot path. We have a JSON decoder that performs 2 to 3 times faster than encoding JSON for tokenization, and 8 to 10 times faster if you're prepared to use the alternative next token API. That's through the careful, the structural analysis of what is this code doing, not through any clever data structures. Literally just saying, what are the costs that we have to pay for each byte of input? Optimizing the hot path to convert per byte into per token, per line, per message, anything that you can do to avoid paying, to convert a cost that you pay for a smaller unit of work, batch it up into a larger one, pays off in terms of your function call. This is the major improvement that we have over the encoding JSON package, is that it in some parts it works per character, where we work per token. And you'll notice how I predicted the outcome of using encoding JSON without even looking at the code. And I really mean there isn't any sleight of hand there. I didn't even bother looking at the code. I just looked at the input and wrote that benchmark before I'd even run it, and it came out to exactly what I thought. And beyond all of this, beyond your setting your constraints, beyond looking at your API design and what that means for the callers of it, what allocations it will push on them, how they can control those. For example, the cost of calling extend can be controlled by the caller by giving a bigger or smaller buffer. Like moving those calls from something which is not controllable, which is inside the package author's domain, to the caller and giving them control over that. All of those, that's the big stones. That's where the big improvements are. Beyond this, once you've done all of these other things, that's when it's time for micro optimization tricks. Moving statements across function calls to make them inline. This outlining trick that move from using a switch statement to a method expression. They gave me the last 15%. They didn't give me the first 800%. They gave me the last 50%, 15%. So obviously you shouldn't be reaching for these tricks, especially at the cost of readability, until you have done the high level analysis, until you've looked at the API design. Because if you do these tricks, you might be able to get a few percent, but you'll never be able to deliver the kind of structural improvements because you haven't addressed the big O order effects in your API. It just won't make any difference. Performance matters sometimes. I want to just put a little asterisk against everything that I said in the last hour, because an efficient JSON parser is, I think, an assumption of anybody who works in a modern language these days. I don't think anyone, like we say, oh, that API call is slow because there's a network transition. It might get cached, like might get dropped or have to be routed to another data center or something like that. We never say it's slow because, oh, it talks JSON. JSON is slow. And so it's an important assumption that we all need to have as software authors, that these primitives of network operations and HTTP and JSON are reliable, efficient constructs that we can build on. And it turns out that there's a couple of times performance in there, in there if you approach it from this way. The thing I want to leave is that this is important work, I think, if you're working at like a low-level foundational part. How important is it for you to do this kind of analysis if you're working on business logic, or if you're working on a front-end controller or something like that, or certainly a piece of code which then makes a network call to somewhere else? I'm going to say it's much less important, because you should focus, because you're probably not spending all your CPU. If your code calls something else over the network, it doesn't matter how many allocations or how much CPU this code uses. Compared to the customer network call, you're never going to see it. So performance matters sometimes. Sometimes it's very important. In the loop, it's very important. When you're in the guts of writing business logic, correctness, readability, and testability are far more important than performance. Just one or two words on further work. Obviously, what's in the future, in better compatibility with encoding JSON, fleshing out the unmarshal story, which is extremely primitive at the moment. I think I can get rid of some of those allocations in next token. They're relatively fixed for the they're relatively fixed overhead now, but it would be good to try and get rid of them. There are a few cases where we actually do touch data more than once. And JSON also has this annoying form of encoded strings, which you've probably never seen in the real world, but annoyingly it's in the specification. So you can put encoded data which needs to be unescaped, which is not currently done. I think we can do this without allocation, because the escaped version is always bigger than the unescaped version, so we can effectively write it over itself. Parse number is slow. It's one of the slowest parts. It's the hardest part to optimize at the moment. Candidate.json is effectively a vector SVG, which is all just JSON numbers. They're Cartesian points on a map. And so scanning numbers is the slowest part there, if not in part because we actually do it twice. To know when the end of a number is, you have to maintain the state machine that tracks from the digit to the fraction to the exponent to know when you're out there. And so we end up reading number twice. One to read it to get the token, and the other one is to give it to parse number to turn back into a float. Surprisingly, there isn't actually that much performance less there. Like, I mean, you wouldn't complain about 170 megabytes a second, but that's only 15%, which is a bit disappointing. And the last one is that I think this idea of reading, this high level idea with a byte reader, are applicable to other kinds of reading and parsing. XML decoding, source code decoding. I think we can use it for HTTP requests. Source code, there's a lot of code that reads and processes source code, and doing that efficiently is interesting. So I think these ideas of scanning a tokenization using this byte reader model of the window and extending it can be applied to many things. So I am, of course, well over time. Thank you again to the organizers for, I emailed them at the last minute and said, can I please have more time? And they were very generous in putting me at the end. I'm gonna hand back to the organizers. I don't know if we're going to do questions here or in a channel there, but I'll let them guide me. So thank you very much. Thank you to GopherCon Turkey for letting me be part of this this evening, and I hope you've had a great day.